Hello. So this quick video is to give you some guidelines on the Handout 7 about the magnetic force. So we come up with this first equation, the F equals QV cross V, while the V is the velocity of the charge Q moving under the magnetic field B. There is a force called the Lorentz force, like this, Lorentz, acting on the charge and with the direction determined by the right hand rule. Okay, so it's just as in this diagram. So suppose that you are having the charge moving in this direction with the velocity v, and when the charge is also under the magnetic field in the direction of the middle finger, the force will be in the direction of the v cross v. Okay, so this look a little bit different, but here we are for the nature. And as a result of this, we consider a case of a uniform magnetic field and with the charge moving with a constant speed. So when the charge is moving with a constant speed in the magnetic field, what you get is you're going to get the circular motion for the charge. And you can calculate the radius of the circular motion from considering the Lorentz force, F, which is equal to the centripetal force, or the Fc, which is the force that is pointing to the center of the circle. So when you always have the centripetal force Fc pointing into the circle, you always make the circular motion. So with the first equation, the magnetic force is the QVB, and the centripetal force as you see from the PHY104, it is the mass times velocity square over the radius, and you combine these two together, you're going to get the radius of the circular motion of a charge under a magnetic field by this equation. Okay, so we come to the example 1. We consider the case for the circular motion of the charge. Okay, so the question gives you the charge Q, the mass M, and they tell you that the charge is performing a circular motion. So when they tell you that it performs a circular motion, you can just simply start with QVB or the Lorentz force equal to the centripetal force, or mv squared over r. Sorry, mv squared over r, which will give you the radius of mv over qb. Okay, and then but the question is not asking you for the r, but they are asking you for the period of motion. So we need to prove that the period of motion is equal to this equation. So we need to look at the period of the motion. So the period of the motion t, we define it as a time for one period or one round of motion, or if your charge or your particle is making exactly one circle, we call this time a period. And what about the distance? Okay, so the distance for one period, it is just the circumference of the circle, which you're gonna have 2 pi r if you have a circle with radius r. And then you can find the relationship between the time and distance by defining the speed as distance divided by the time. So finally, if you rearrange the equation, you're going to get 2 pi r over v. And then with the circular motion, you can use the fact that you get from the circular motion. to finally derive for the period. So 2 pi over v times mv over qb. You cancel the v, and finally you should get the period or t as 2 pi m over qb. So it's q it is for this. And then we come to the question 2. A particle undergoes uniform circular motion in a uniform magnetic field, so we consider the same problem again, but now the equation has given you the radius of the circular motion. So this is what they give you, and then they told you already the magnitude of the force. Then what is the kinetic energy? So the last sentence means that they ask you for the kinetic energy, for the expression of the kinetic energy. So in this case, we need to write down this kinetic energy, EK, in terms of the variable that the question has given. So you need to write down the EK in terms of F and R. Okay? So how can we do that? Where could we start with? Okay. So we could start with a circular motion again. So where I have the Lorentz force equals to the centripetal force, or I have the QVB equals to mv squared over r. So cancel v and cancel the v, and you get the r equals mv over qb. Okay, and then from here you can try to rearrange the equation. So we're trying to make the expression for the EK, which equals to half mv squared, and then you can recognize the mv over here. Okay, so what I would do is I try to rearrange the equation like this. I will start with mv equals qbr, and when you want to get the half mv squared, you just times this equation by half v. So times mv by half v, you're gonna get the half mv squared, and on this side you're gonna get the half qvb and times by r. And you can see that the qvb here, it is actually the Lorentz force, and half mv squared here is actually the kinetic energy. So finally, you come up with the expression EK equals half FR. Okay, and then after substituting the values that the question has given you, you should have your answer in the unit of joule. Okay, and then question 3. Now we are considering a helical motion. So let's talk a little bit about the helical motion. So a helical motion is something like this. So it is actually made of a circular motion plus the linear motion. To set this straight, when you have a circular motion, the trajectory of the particle will look like this. And then when you have a linear motion with a different direction, the trajectory of your particle will look like this. And if you add up these two motions together, it will just give you the helical motion. Okay? And then with the helical motion, we are going to define a pitch distance. Okay? So the pitch distance is the distance in, let's say, the x direction, that when you do a circular motion on the y-z plane, here the y-z plane, how much distance do you get for the x direction? So we call this the pitch distance. Okay. So let's have a look at this problem closely. Okay. They say that the mass m and the charge e is ejected from the origin at velocity v at the angle theta with the x-axis. So the angle theta is the key from here. So if I try to flip this plot so that I have the x-axis pointing to the right hand side like this, and then let's consider the velocity v. So the equation says that velocity v is making an angle theta with the x-axis. Okay, so here's what I have. So if I get the x component and the y component of this velocity, I can say that the vx or the x component of the velocity is v times by the cosine theta. Okay, and then I can calculate the pitch distance from that velocity, or I can say that it is a horizontal velocity times by the time for one period. Okay, so time for one period, it is the thing that we have already calculated from the example 1. So you need to go back and see how we calculate the time for one period from example 1, and you can use the answer from the example 1. So here I would say that the pitch distance, or x, is the v cosine theta, and the time for period 1, for one period, sorry, yeah, what we have is the 2 pi m over qb. So you can just plug that into your equation. Okay, and this is your answer. Yeah, easy. Yeah. So example 4, two isotopes of helium nuclei, He3 and He4, accelerated through the same potential difference. They enter the regions of uniform magnetic field at S2 and follow a semicircular path. So actually, semicircular path is actually the circular path. So there's no doubt about that. And the helium-3. So we need to define the charge of helium-3 as plus 3e. And also the charge for the He4 nucleus as plus 4e, or 4 times the charge of the proton. And also the mass of the helium-3, we can say that it is 3 times the mass of the proton, or the 3u. And the mass of the helium-4 is 4u. So the question asks you to determine the ratio of the radius of helium-3 to the helium-4. Or they ask you to find the ratio between the R He3 divided by the R He4. Okay? So now, with this information, how can we get this ratio? So again, we consider a circular motion. Okay? So I try to do this every time, because in the exam you probably want to do this. Okay, so not just remember the formula R mv equals qb, but you need to prove from Newton's equation as well that for the circular motion, the Lorentz force will become the centripetal force, and hence the radius of mv over qb. Okay. So from the mv over qb, so we can do like the radius of helium-3 divided by the radius of helium-4, and for the denominator, the radius of helium-3, so which is mass which has the mass of 3u, and times the velocity v, and the charge, it should actually be 2e because it is the nucleus of the helium. So sorry, this is not 3e or 4e, but it's only 2e because the nucleus has only 2 protons. Right. So this will become 2e times by the magnetic field B. And here for the denominator, you have the mass for u times the velocity v and divided by the charge 2e and divided by the magnetic field B. So when the magnetic field and when the velocity kept constant, we can cancel all those, and then we can cancel the constants from the proton mass and proton charge, and we cancel these two. So finally, you can come up with the ratio between the radius of helium-3 and helium-4 as 3 to 4. Okay, so this is a principle of the mass spectrometer. So when you have the different types of nuclei, and your nuclei is undergoing the magnetic field, a circular motion within the magnetic field, you have the difference in the radius of the motion that you can tell the difference of the type of your nuclei. Okay, and then we come to number 5. So here we look at the relation between the magnetic field and the electric field. So when an electron or the negative charge is traveling inside this device, okay, let's say it's the device, and you can see that there is a positive charge here and negative charge here, so it looks like two double plates, which will give you the electric field, and also you also have a magnetic field over here. So when a negative charge is inside here, it will undergo a Coulomb force Fe. So it will be drawn to the positive charge. But if we look at the effect of the magnetic field, so when you use the right-hand rule to determine the direction of the force, so with the positive charge, you should get the magnetic force or the Lorentz force in the upward direction, but with the negatively charged, you should get the Lorentz force in the downward direction. Okay? And then the question says that the charge entered the regions with perpendicular electric field and magnetic field chosen such that the electron move along a straight line. So the keyword here is straight line. So So this is misspelling. It's not straight line. It's straight line. Okay. So when it is moving in a straight line, so that means that is no net force up or down. Or we can say that the force from the Coulomb force is equals to force from the Lorentz force. And then how to find the this force? Okay. So an electron is accelerated from the cathode to anode through a voltage V. So in this case, we should have, so this is a cathode and this is the anode. And there is going to be a potential difference V apply across the anodes and the cathodes. And then from the conservation of energy, we should start with the potential energy of the electron is transferred into a kinetic energy of the electron when you apply the voltage to accelerate this electron from the left hand side to the right hand side. So the potential energy is given as the charge of the electrons times by the voltage that is applied to your electron, and it will become the kinetic energy by the half mv squared. So so this means that you give the voltage v to your electron and you can accelerate the electrons to have the velocity v. Okay? And then after that, we go back to consider this equation, the equilibrium between the electric force and the magnetic force. And for the electric force, let's consider the electric field E over here. So when your electron with charge E is within the magnetic field, the electric field E, it will give you the Coulomb force of the charge times the field. And then when you have the electron moving perpendicular to the magnetic field, or if the V is perpendicular to B, you are going to have the Lorentz force with the magnitude EVB. Then you can cancel the E, and then you can consider the the relationship between the field E and the field B. And then what I would do to get this relation, or here it is you try to determine the ratio between the charge per mass of the electron. is when I have the relationship from the conservation of energy. So when you see the V square over here, I'll try to also make the V square over here as well. So what I do here is I will do the square for the whole equation. So we get the E square equals V square times B square. And then from this equation, EV equals half mv squared. you can rearrange the equation so that you get the v squared as 2ev over m. Okay, so finally you combine this equation and this equation together. What you're gonna get is the expression of e squared which now you already have the ratio between the charge and the mass inside. Okay, so finally what you do is you just need to rearrange the equation again so that you have the E over m on the left hand side and the rest on the right hand side. And that's going to be the QED for you, okay? So the key things, the key ideas for this problem is you can apply the conservation of energy. So when you apply the conservation of energy, you have the velocity. And then when you have the velocity, you can then consider the Lorentz force, okay? And then finally it will just give you the ratio between the electron and the mass. Okay, so the next topic, it would be the Hall effect. The Hall effect is pretty much the same as the phenomena that we just discussed. Okay, so we consider a material, an electrode here, where we inject the electron or some of the electric current into this object, and this object is also in the magnetic field. So when the electron is or the hole is flowing within the magnetic field, so of course what will happen with the charge is the charge will make a circular motion, and then after the charge is making a circular motion, so the negative charge will be on one side and the positive charge will be on the other side. So what you get from this is you're gonna get an electric field in one direction, or in this case it's in the Z direction, which is perpendicular to the magnetic field, in which the magnetic field you are given in the y direction. Okay, so it would be pretty similar to the equations that we discussed before. Okay, so when you get the electric field and when you get the magnetic field, if you have the right ratio between the electric field and the magnetic field, what you can have for a charge is your charge can be moving in a straight line if the force from the electric field is equal to the magnitude of the force from the magnetic field, or Fe equals Fb. Okay, and then from the Fe equals Fb, you can derive many equations from this. So using the relation that from the Handout 5, and the definition for the electric current, or the definition for the current density, as J is the current divided by the area. Okay, so you can come up with these kind of relations. Okay, so now let's try example 6. Okay, so they give you all the parameters. So they give you the size of your electrode, the width and the thickness, and they give you also the current, and they give you also the magnetic field, and then they tell you that the whole voltage, okay, the whole voltage is the voltage between between the negative charge that is accumulated on the left hand side and the positive charges that is accumulated on the right hand side. So if you get a voltmeter to measure the voltage across these two sides, the voltage is called the Hall voltage or the VH. Okay, and they also give you the Hall voltage. Okay. So in order to find the density of the free electrons in this metal, okay. So with the current that can be measured, okay, we assume that the charges are moving in a straight line. In order to provide the current. Okay? So we need to understand this concept. This is very important, yeah? Because if you consider the object with the Hall effect, okay, and then you got charge accumulated on the two sides, and then you put this in a magnetic field, okay. So if the magnetic field and the electric field from the charges are not balanced, what you get is, if an electron coming into your object, your electron is just going, it's just making like a circular motion, and the hole is also making some circular motion. Okay, so with the circular motion, your charge is never coming out. So when the charge is never coming out, you have no current. Okay? So again, when you need the current, your charge need to move in a straight line. Okay? And then when you need a straight line, you're going to need Fe and Fb to be equal. Okay. So now let's start from this expression, Fe and Fb. So Fb, when you got the charge from the electron moving with velocity v and moving in a magnetic field B, you get EVB for the Lorentz force. And then under an electric field from the Hall voltage, okay? So you should get the Coulomb force by the charge times by the electric field. And with the electric field, so I will also call it the EH, or the Hall electric field. It is actually the Hall voltage divided by the distance. So the distance between the side with full of positive charge and full of negative charge is the W. Okay? So here we can say that the Coulomb force is E times the Hall voltage, and then divided by the width of the object, or the W. And then if you cancel the E, you can get the expression for the velocity. Okay, so you can say that the velocity of the electron moving in a straight line is V equals VH over W, and then divided by B. Okay, so I'll call this the drift velocity. So this is exactly the same velocity that you have in the I equals NEVA. So this is also the drift velocity. Okay? So then what you do is you just substitute this drift velocity into this equation so that you get the NEVH over BW times by the area A. So the area A in which the current is flowing through, this is the area A. It is the width times by the thickness T. Okay, so this will become WT, and then you can cancel the W. Okay, so finally, the question is asking you for the density of the free electrons. Okay, or let's say it is the N. So you can rearrange the equation. You have the N equals I times B, and then divided by the charge E and the whole voltage and the thickness T. Okay, so you can you can substitute all the values. Okay, you are given I as 78 ampere. It's quite a lot of current actually. It's quite large current actually. And B you are given as 2.29 Tesla. And E is the electron charge. And VH or the whole voltage is 130 microvolt. And T is the thickness. So you got all the variables, all the parameters needed. And then the density should be found in the unit of per cubic meter. Okay? And then we move to the topic of the magnetic force on the current carrying a conductor. So you have a conductor I, sorry, the conductor with the current I, which is also you can say that it's the current density times the area. So the current is moving upward here. So suppose that it has the velocity v over here. And then when you have the charge moving with velocity v on the magnetic field B, you can use the Coulomb force. Sorry, it's the Lorentz force to calculate the force acting on the charge. And then after you derive this equation another time, okay, you can write down the Lorentz force in the other form. Say, okay, so it could be the I L cross B. Okay, so this vector L, it is in the similar direction to I. Is the direction that current flow, and B is the direction of the magnetic field. So from the right hand rule, in which you can practice by yourself, you can get the direction of force going to the left hand side. Okay, so let's come to example number 7. So a wire carry a current 10 ampere, right? So here you are given I over here in a direction that makes an angle of the 30 degree with the direction of the magnetic field with the strength 0.3 Tesla. Okay, so how to picture this? So we start with making a picture of a magnetic field. It's a B. And you can draw a wire. Yeah, oh, it's not a good angle. Yeah, like this. Okay, so this is a wire. And this wire is making an angle of 30 degree with the direction of the magnetic field. Okay? And also it's also giving you the length of the wire, L. Okay? So in this way, the length of the wire will become the vector L. Okay? So using the F equals IL cross B. Okay? Here, you'll be able to find the magnitude of the force F as the current times the magnitude of the length times the magnitude of the magnetic field times the sine of the angle theta. Okay. So with all the parameters, with the I, with the L, and with the B, and with theta given by the questions, you should be able to find the force in the unit of Newton. Okay? And then for the question 8, it is a combination of the Lorentz force on the wire with Newton's equation with the equilibrium. Okay? So the question asking you what current must exist in the conductor for the tension in the supporting wire to be 0. Okay? So with the 0 tension of the wire, you can just cut off the wire, and your metal wire here is still in equilibrium. So this is the meaning of this. So when it is in the mechanical equilibrium, you want to consider mg, and not only the mg, but there should be also the other force, which is actually the Lorentz force Fb, that is acting on the wire to keep this system in the equilibrium. Okay, so you can come up with an easy expression. So you can say that Fb is equals mg, and then whenever you have the L, okay, or the displacement of your current perpendicular to B, okay, because B is pointing in and L is pointing to the right hand side, so it's perpendicular. So you can simply write down the magnitude of the force as the ILB equals mg. And if they ask you for the current that must exist, you can just rearrange the equation and you should get a current in the unit of ampere. Okay, so about the last one, but not the last one. Now we consider a rectangular loop ABCD. So this example is resembled to tutorial 7, and it is a principle of a motor. So a rectangular loop ABCD is placed in the uniform magnetic field B parallel to the plane of the loop. So you have the magnetic field to the right hand side, and then you have current here going up the current at the BC going to the right, the current at CD going down, the current at the D is also going to the left hand side. Okay. So so with the expressions of Lorentz force, FI cross B. So whenever you have the L in parallel with B, or if you say that sine theta is 0, or the sine theta is pi, oh sorry, that's if I say that theta is 0 or theta is equal to pi, is 0 or pi, yeah, you can say that F, or the magnitude of the force, or the ILB sine theta will become 0, okay? So at the BC, I can say that the force at BC is 0 and the force at CD is also the 0 because there are the cases, okay? But for the force at AB and for the force at CD, if you are given that CD and the AB has a length A, okay, we can easily say that the magnitude of the Lorentz force at the AB side and at the CD side will become the current times the length and times the magnetic field, okay? And using the right hand rule, you can say that the direction of the force at the CD is, so when you got the B to the right hand side and L going down, so L cross B will give you the F out from the paper, going out from the paper, and vice versa. At AB, you get F that is going into the paper. Okay? But the question, they're not asking you about the force, but they ask you about the torque. Okay? So you can say that the magnitude of the force at AB and CD are equal. Okay? So in order to calculate the torque from the system, okay, I just turn this system around. Okay? So I'm just looking from the side view of this system, where the magnetic field is still on the right hand side. But the force at AB is now going down, and the force at CD is now going up. Okay? To calculate the torque, yeah, you can just choose any points on the system, any point on your arms as a pivot. Okay? And then firstly, you are given the dimension or the size of your wire, or the size of the BC as small b here. Okay. So here, the torque will be given by you timing the distance b with the force at CD. Okay. So the magnitude of the torque will become the IAB times the magnetic field. Which is your answer. Okay. And then we come to the last question, the example 10. They say a conducting cylinder has a total charge Q uniformly distributed on the curved surface. How can we picture this? Okay. So we got a cylinder, and we got the charge uniformly distributed. So you see the positive charge everywhere, and the total charge is Q. And then this cylinder is rotating. Okay. So that if your cylinder has the radius of r, yeah. So when I look at this cylinder from a top view, yeah, and if I consider a charge q over here, your charge will move with a tangential velocity of omega times r. Okay? And then, when we consider a uniform magnetic field B parallel to the cylinder axis, yeah, your magnetic field will be in this direction. And here, it can be either coming out or going into the paper. So this is magnetic field. Okay. So here, what we get from this is we know that the magnetic field and the velocity is perpendicular. So what happened after this? We can calculate the magnitude of the force by simply using QVB. So in which, if we consider all the charges in the system, we have the total charge Q times by omega r and times by B. And if you want to find the pressure, we can just simply divide the force by the area, okay? So which is Q omega RB, and the area of the cylindrical surface, cylinder surface, is a 2 pi r, 2 pi I circumference, and the L is the length of the cylinder. Yeah. So we cancel the r over here. So finally, we're gonna get this expression for the pressure. Okay. And here's your answer.